Okay, let's begin our new topic, shear strength. So my question is, why do we care about shear strength most? Shear strength is one of the most important soil properties to control soil behavior in mechanics. This shear strength is required to estimate bearing capacity. The shallow foundation failure mode looks like that. It looks like sliding, right? And slope stability. This way, this way, this way. And tunneling and retaining walls all are failed in a shear mode. Shear failures. So this failure can be determined by shear strength of the soils. Later on, we can closer look at this area. And then very interesting things in our soil mechanics is totally different behavior in soils compared to steel and concrete. This soil failure can be determined by shear strength with the incorporation of presence of poor water pressures. But steel and concrete, they don't have any additional components to consider in their strength parameters. So steel and concrete behavior is very expected. Yes. But soils, quite unexpected. Uncertainties. We have a lot of abnormal behavior due to poor water, poor air. So soil's shear behavior and shear strength is quite complex. So let's take a closer look at the failure surface. This is a theoretical failure surface and actual failure surfaces. Our geotechnical structures failed in this way, always. So you can see this resistance force against driving forces. They are all the opposite directions. This soil mass tend to move this way, sliding. But the other way, we have resistance force in the opposite directions. Once they were balanced, this slope, this footing, very stable. But this driving force greater than shear resistance, unfortunately, this slope and footing will be failed. Another geotechnical structures, retaining wall. Yes, next module of geotech is a geotechnical engineering module. You will learn about design of retaining wall with respect to earth pressures. This is a soil. This soil, their self-weights. Sometimes we call in this way is soil pressures, earth pressures acting on retaining wall, vertically and laterally. This retaining wall should resist such stresses and pressures. So right now, the retaining wall resists certain loads from behind horizontal earth pressures. Very safe. But, yeah, due to external load, due to rainfall, or excavations, retaining wall moves and showing shear failures, something like that. This is a failure plane, and then this is the driving force, this is the resistance force. Hi, Prof. Is it has happened really in real situations? Yes, yes. I'm not very proud to say that if let's say we don't really understand the earth pressures and then certain retaining wall design and soil mechanics properties, probably major incidents will happen like this. In 2007, we have two critical accidents. One is the high-rise building construction site, International Finance Center, IFC building in Seoul. And the other one is a railway, high bullet train site. Their excavation depth is more than 50 meters. Your height is roughly 22 meters. Wow, 50 meters is quite deep, very huge excavation work. The inside is our construction site, outside is the residential area. But some reasons, the retaining wall collapsed. It means that these retaining wall structures couldn't withstand such pressures coming from behind the soil. So when I was in master and PhD courses, I was involved in the investigation team. Why it happened? So in this case, we have certain questions. What is the distribution of earth pressure acting on the structures? What is the required embedment depths and thickness of the retaining structures in order to give the accurate factor of safety against collapse? And what are the movement of surround grounds? But it is very important to avoid damage to adjacent buildings. And then, can the design be improved by any use of the ground anchors, something like that? We can visualize the earth pressures. This earth pressure looks like geostatic pressures. You know, geostatic pressure is a vertical stress, right? Self weight. Your weight acting to gravitational direction, right? Which is the vertical mostly. But horizontal earth pressure is lateral pressures. Resultant force of triangle vertical stress. Probably our Korean designer omit this magnitude of lateral earth pressures. That's why soil's shear strength always governs our safety and geotechnical structures safety. How do we measure? We have certain approaches. Before we explain the different approaches, we need to answer these questions. What did you say when you are asked, soil is a continuum or not? This is our grains. This is the same images. This is the simplified configuration of our soils. It looks individual particles, but considering our soil as a continuum is a quite fundamental approaches in our geotechnical engineering, allowing certain application of continuum mechanics principles to solve complex soil structure interaction problems. Now, you attended physics and mathematics, right? All theory is based on continuum mechanics. But our soil quite discrete, so we couldn't apply continuum mechanics to our soil mechanics. Wow, so sad. But we just make assumptions. Soil behave as a continuum materials. I know these assumptions sometimes has limitations, but from these assumptions, we are able to solve many problems in our soil mechanics. So, in our soil mechanics, this sign convention is quite crucial for consistently defining our stress and deformations. In our soil mechanics, compression is a plus, positive, tensile tension is negative. Quite different from structural engineering. Because our soil is only resists compressive soils. And tensile resistance is significantly less. So when I describing soils shearing behavior, we need to understand these 5 different simple concepts. Don't be serious, just try to understand. First one is volumetric deformations. Volumetric. Volume related deformations. So just tell me about whether it is make sense or not. I dive into swimming pool. I felt some pressure, which is the hydrostatic pressure, right? And then due to these pressures, my cheeks, my head's a bit decreased, contracted, but my body just remain constant. Does it make sense or not? Sounds weird. How come only my head contracted? Volumetric deformation meaning remain their shape constant. All round pressure acted on every surface. Okay. Second is shear deformations. Refers to change in shape of the material due to applied shear stress without a significant change in volume. Volume remain constant, but I have a certain shear loadings. The face shape is something different. Volume is same. Only the shape is different. In soil mechanics, understanding this shear behavior is essential for analyzing and predicting behavior of our soil under certain load. So you can see apply particular load. The red one is the deformed shape. How about rotate and press again? Shear deformations. And then it is also part of shear deformation, but in an elastic range and plastic range. Intuitively, you may understand, right? After removing certain loads, elastic behavior recover back to original shape 100%, but plastic shear only 90%, 80%. It depends on the soil's Young's modulus and Poisson ratio, right? Yes. I believe you may understand the elastic and plastic behavior. You studied in a structural module, right? Same. Yes, same. And then drain or undrained. Can you even understand drain or undrained meaning? During the life of our geotechnical structure, we have to consider drain and undrained conditions to figure out real behaviors. So decision on what shear strength parameter to use depends on whether you are considering the short-term or long-term conditions. Your structure is temporal, your structure permanent. The drained shear condition refers to situations where you apply the pressure with the soil has time to dissipate during the application of certain load. It is typically occurs in the soil with a high permeability or under slow rooting conditions. Yeah, quite intuitive. Then we can obtain drained properties. water drain out. No water pressure, which is the effective shear strength. Long term or slow loading. On the other hand, in the short-term conditions and soil with low permeability do not have sufficient time for the excess water pressure to dissipate. Our marine clay, even you apply very slow pressures, there will be excess water pressure developed. No choice due to low permeability. And you're loading quite fast. Suddenly your water pressures developed resists your shock load. It means that you will have water pressures. That's all. On drain, you have water pressure. Drain, you don't have water pressures. Dilation is something like you gain your weight, bulk up. Simply, this phenomenon is dilations. When you take a look at the stress-strain relationships, if the soil shear strain keep increasing without any further shear stress in the soil, we can call critical states. Your strain increase, but your stress increment is too small. It means that soil already failed and just fail further and further. So this around soils, the soil around this status is called critical states, very critical states. And let's take a look at the green one. This is very loosened soils. When you apply your load, your loading increase, your volume change also increase, and then stop. Stress strain looks like something like that, getting harder and harder. Your volume decrease, steadily decrease, which is the loose soil conditions. But when you take a look at lead, initially it get contracted. You see here, from here to here, a bit contracted. But soil particles slide over. You see the gap? Suddenly volume increase. This effect is the dilations and increase shear strength of soils. So large normal effective stress tends to suppress dilation effect sometimes. Increase, but your high pressure crash down again. But tend to slide over, but your high pressure press down again. So very high normal pressures sometimes suppress the dilation effect, but normally slide over. So you see, after initial contraction, suddenly your volume increase, and at the at the first of a contraction point, you can hit the peak and then hardening behaviors. This is the dense conditions. Already packed, already thoroughly packed, and then you press, and then your volume initially contracted and then slide over, increase. Okay, let's take a 10-minute break and then we can continue. So when you take a look at the failure surface on the left-hand side, so the particle has already rolled and slid each other when the shear stress are large enough. It means that there will be a considerable deformations and with shear failures. Okay, let's simplify the certain problem in our physics. Here is a simple model for shear strength of the soil using Coulomb law. Have you heard about Moore-Coulombs? Moore is another researcher and Coulomb is another researcher. So we utilized two theory to express our soil's behavior. One is the Coulomb law, Coulomb's friction law. T is the horizontal force. N is the normal force. Okay? And then mu is the friction coefficient of static frictions between block and table, which is the tangent phi, which is the friction angles. The maximum friction resistance is mu n when the horizontal force is greater than this. Then the slip is initiated. And then rewrite the above the equations in terms of stress while the block just slipped. And then we can express in this way. The A is the area of the plane parallel to this external horizontal loads. F is the denote failures. This theory can be applicable to soil particle as well. Tau shear force, sigma is a normal force, and then we have certain relationships. It looks linear, but initially we have certain volume increases. So what is the failure? We need to consider and think through the definition of failure in soils. And then actual failure is very complicated, but in our soil mechanics, our stresses in the combination of shear stress and normal stress, and then move around our stress conditions here. Now it's here. And then after certain loading conditions, this point move here, and go around, and then touch this line. Then we can consider as a failure of the soil. And then Moore and Coulomb define this failure line. That's why in our soil mechanics, Moore-Coulomb models, so-called MC model is widely used to capture soil's failure behavior. This is another plane, same plane, shear stress and normal stress. And right now I'm stuck with point A or point B. And then loading just applied. My stresses, normal stress and shear stress developed. So right now assume this point and this point, this point, these points. We follow this track, total stress path. And then we follow this track, effective stress path. Hey, bro, what is the difference? Developed port pressures. After later on, I will explain, but under this failure line, we have a lot of circle. Researcher Moore proposed these theories. All stresses in soils represented by circle. So we so-called Moore circle. Hidden circle here a lot. So currently my circle is here, but increases the stress, the circle's radius, diameter increase, and just touch this line, we so-called fail. But simply, my condition is here, and reloading here, unloading here, and suddenly water comes in, my behavior something different, but still here, and then, wow, more pressures, and then touch. You see, this is a failure line, and this is a failure point. My soil just failed with the combination of certain shear stress, certain normal stress. Yes, we need to find out these combinations. So, Moore and Coulomb. Moore represents a theory for rupture in materials, that material fails because of a critical combination of normal stress and shearing stress, not from either max normal or shear stress alone. This is the Moore suggestions. And Coulomb assumed that it is sufficient to approximate the shear stress on the failure plane as a linear function to normal stress. Linear. So Coulomb's law require the existence or development of critical sliding plane, so-called slip plane, failure plane. Yes. So still we have same axis, shear stress, normal stress, and straight line of the failure. And then the C is cohesion. Pi is the internal friction angles. Sigma is the normal stress on the failure plane. Tau F is the shear strength of soils. This is the Moore-Coulomb failure criterion. This tau F is C plus this height. From here to here, C here. From here to here, sigma tangent pi. In a saturated soil, the total normal stress at a point is the sum of the effective stress plus port pressure, right? So the effective stress is carried by the soil particles. So the MC criterion can be expressed in terms of effective stress as well. Keep that in mind. We have a lot of hidden circles. Later on, I will show you. So this point from here to here is C prime. From here to here is sigma prime tangent V prime. Yes, C prime plus from here to here, sigma prime tangent phi is this height. So this equation is expression of the shear strength that is comprised of cohesion and friction angle and normal stress. The value of C prime for sand or inorganic silt is more like 0. Because sand is something like no cohesion materials, right? For the normally consolidated clay, C prime also approximately 0. And over-consolidated clay has a value of C prime. This internal friction angle phi prime is sometimes referred to as a drain angle frictions. Typical value of this phi prime is something angular soils ranged from 26 to 45. So again, cohesion component here, and then friction component here, and linear. A little bit different perspective. I express a Moore-Coulomb model in a sigma x, sigma y, sigma 3 axes. And then their failure shape is something like we have a specific sharp point. So when you select MC model in your numerical simulations, sometimes your stress just at this corner, they don't know where to go, here and here. That's why there should be some error. So, numerically, we implement this model as a bit different shape, a bit curved shape, rather than sharpened shapes, just for your informations. So, I explain the stress state in our slope, in our soils. This is soil element, and take this soil element sigma 1, sigma 3. Confining pressure and additional loading. This is the sigma 1. Sigma 3 is the confining pressures. Typical loading stress conditions. Due to this loading, this soil element start to fail with this failure line. Mostly failure line with certain angles. When you take a look at the failure line, we have shear stress and normal stress. This is the outside pressure. This is the internal stress of the soil elements. So mathematically, the internal pressure of the tau and sigma can be expressed by this. And then we can merge these two equations into one. I don't ask you, hey, please write the shear stress and the sigma. I mentioned to you, I don't test your memory capacity. Even your second quiz, you can bring your cheat sheet. Okay? Same stress, soil element, your external load, and you have internal stresses, tau and sigma. Let's draw a circle for this stress state. Here is the sigma 3 minimum. Here is the additional vertical load. So sigma 1 is greater than sigma 3. Then we drew the circle with the diameters, the differences of the sigma 1 and sigma 3. These stress conditions represents, this Mohr circle represents these stress conditions. That's all. This is the Mohr circle. And then column propose straight line, right? Oh yes, straight line. After heavy rain, this slope will fail, sliding to right to left. And your soil resists left to right. This is a potential failure line. Only this line will fail. This element location, Y location, looks stable, right? Why? Only this area fail only. So your Mohr circle, this element stress state is something like that. Sigma 3, sigma 1. Draw the circle, but this circle haven't reached failure line yet. But when you take a look at the failure line, even your sigma 3 is small, and your sigma 1 is a bit greater than Y, but your stress combinations already touched failure line. That's why this X location is the failure. Let's consider simple plain ground conditions. Sigma H is confining pressure, which is the sigma 3, and vertical stresses, which is the sigma 1. And sigma H, sigma V, we draw the circle. Okay, very happy. Apply surcharge. I don't know why, but your contractor dumped soil mass, so your muscle increase. Wow, hi prof, this sucker still didn't reach yet to the straight line. Correct, correct. Your soil still safe. This soil element does not fail if the more circle is contained within the envelope. But keep on increasing, your more circle increasing, and the width touching the failure envelope. This slide just explained to you total and effective stresses. Every stresses can be represented by more circle. This is the total stress, sigma H, sigma V, total stress. But this soil fully saturated, there should be some poor water pressures. This is the poor water, sigma V minus poor water pressure is effective stress. And we have another more circles. This circle represents effective stress. This more circle represents total stress. This total stress include poor water pressures. Same, total stress equals to effective stress, poor water pressures. This stress state represented by this more circle. Then we can draw the straight line. Just touch our more circles. That's why more Coulomb model. This is the failure envelope for total stress. This is the failure envelope for effective stress. Almost there. Sorry. Just focus. Same soil elements. And then in notch. Sigma 1, sigma 3. This soil element will be failed according to this failure line. These stress states can be drawn by more circle, right? Okay, here is sigma 3. Here is sigma 1. Draw the circle and draw the straight line. Okay. So far, okay. We are on the same page. This is what I just explained to you. But in this slide, we have a lot of formula. But trigonometric functions only. You can consider this triangle. We have sigma 1 minus sigma 3 divided by 2 is the radius. We know this length. We know the angle. Then we can get the length of the this and this. Just represents certain length of the triangle based on trigonometric functions. So C prime cotangent P prime plus sigma 1 plus sigma 3 divided by 2. This line times sine prime is this. See, right? This equation just represents this times sine P prime is this length. That's all. And we can also convert this equation into principal stress, sigma 1, sigma 3, and V prime, V prime. Again, I don't test you your memory capacity. Just make sure that how do we get this? And then you solve this equation, not the solve, move around parts to the left, to the left, and then to the right, and then rewrite this equation, yields these equations according to this process. Just give it a try after these lectures. Just reminds of your mathematics fundamentals. Simply get these equations. So today, I will explain to you these two tests. And mostly, we employ triaxial tests. So just briefly explain what is the direct shear test is, and then explain to you triaxial tests one-third. And the next week, we can continue to the discussion of the triaxial tests. This is the way we obtain soil's shear strength. This is the field. I didn't apply anything. These soil elements just have horizontal and vertical. The vertical one is our total vertical stress. How do you know? Unit weight times jet, which is the sigma VC, vertical compression. How do you know the horizontal? We have a horizontal coefficient, mostly 0.5. In your geotechnical engineering module, you may study retaining wall, which is the lateral earth pressures. How do you get this lateral earth pressure? From the horizontal vertical effect, vertical stress, then times coefficients of lateral earth pressure, range from 0.4 to 0.6, but now assume 0.5. So this whole condition is natural geostatic stress. But putting shallow foundations, it means that my vertical stress increase. And then in order to design this shallow foundation, need to know shear strength as it is. It means that in your laboratory, you copy this stress condition in your lab, right? So right now, I take soil sample. Now, no pressure, only air pressure, right? Now is the lab. Just this condition. Just this condition. And then apply confining pressure, geostatic pressures. Then what's the next? We expect putting load. We simulate vertical load or same, right? Rotate vertical, rotate horizontal. This is our laboratory test. First one is a triaxial test. Second one is direct shear tests. In our direct shear test, we have certain equipments. We prepare our soil specimen and then we can force to push to get our soil filled. Very simple. And then we follow BS, ISO, ASTM. And then we also control the loading rate. Slow or faster? How do we know? According to testing standard, British standard, international standard organizations, and American Society of Testing and Materials, something like that. Now, I'm happy to share with you triaxial shear tests, so-called triaxial tests. One of the most reliable method available for determining shear strength parameters. C pi. It is widely used for research and design practice. So we prepare soil sample with the specific dimensions according to standard. And then this soil sample is encased by very thin rubber membrane and placed inside the plastic cylindrical chamber that is usually filled with water or air to apply confining pressures. So our school equipped the machine with air pressures. So we can apply cell pressures, just apply air inside the chamber, and that pressures directly acting on our soil sample. And then we apply back pressures. Back pressures? What is the back pressures? Why do we need applying back pressures? Hi, Prabhu, back, what does that back means? Just name. No physical meaning. These back pressures link to directly to soil. This is the water pressures. Simply, we inject water to soil. Cell pressure is the air outside the soil sample inside the chamber to apply confining pressures. Back pressure is the water injection to soil sample. Why? I will ask this to second quiz. In order to get answer, you may want to read off the additional reading materials I just uploaded on top of the lecture material. The specimen is subjected to confining pressure by applying air pressure in the chamber. In these stages, we can decide whether to open the drain valve or not while maintaining confining pressures. Once you open, it is consolidated, close, unconsolidated. Consolidated meaning water drain out. So if you open your valve at the bottom, water drain out. So we so-called consolidated. But when you close the valve at the bottom, water cannot be drained out. So undrained, sorry, unconsolidated. Secondly, to apply the shear stress at the on top of the soil sample, we must apply axial stress, something like that, external loading, normally so-called deviator stress, deviatory stresses. In this case, we can also decide close the valve or open the valve. In this case, we can drain loading on drain conditions. At failure, we can observe the failure line. This is a real testing result. You see your soil sample, apply, and slide down. Slide down. This failure plane, exactly same as what we just discussed. This stress status can be drawn in terms of Mohr circle. So summary, when you we have two steps. Now I can say two steps. First one is open valve, closed valve. Open one is consolidated, closed one is unconsolidated. During the consolidation stages, and in the shearing stages or loading stages, you can also open your valve, it is drain conditions. Close your valve, it is on drain conditions. So consolidated drain condition, CD tests. Consolidated on drain tests, CU tests. Unconsolidated on drain condition, it is UU test. We have three different types of tests. And I will ask you, please explain details of UU tests, CD tests, CU tests. Triaxial tests we followed by specific standard. Today, I will explain CD tests first, then stop and continue next week because mechanism all are same. So I will ask you to think through the remaining two tests, CU test, UU tests, according to what I'm gonna explain you right now. Let's begin. CD tests, consolidated drained conditions. Total stress equals to effective stress plus poor water pressures. Okay, let's begin. This is the consolidations. Stages. Apply load. Confining pressures. My valve at the end of the bottom open. During the consolidation, water drain out. It means your water pressure, 0. It means your effective stress exactly identical to you just applied. What you just applied. So now is the total, but no water pressure. It means this became effective stress in the consolidation stages. After consolidation, we apply shear load, which is the shearing stages. See, only increase vertical load, but still open your valve. I'm expecting due to this loading, there should be some excess water pressures. Soil is already saturated. So you apply additional load, you will get excess water pressure, but open your water pressure still 0. So your effective stress, this one plus this one. At the end, this loading, particular load, keep on increasing, reached failure load. Just change sigma F, then you will get, you completed your trial test, technically CD test. We have 2 stages right now. Consolidation stages, shearing stages. But I just mentioned to you, soil specimen basically saturated. But hi prof, how to get my soil saturated? Before preparing specimen, we put the soil specimen into the water, suck into the water, so we can get saturated soil sample? No. What we have to keep in mind is that we managed to get the soil specimen saturated before consolidation stages and shearing stages. How do we make our soil saturated? Can you remember back pressures? Back pressure is the injection of water to the soil specimen. So we just inject back pressure into the soil specimens. It means that this is soil. So I inject, okay, top. The valve is something like that. Line is connected to the here and inject water. So water keep inside, keep injected. What would you say? The soil sample stable or unstable? Only applying back pressures, your soil will fail. This is the specific steps to make our soil saturated. Once you prepare your soil sample and put it in your chamber, treasure cell and apply the chamber, right? And then you apply cell pressure first, which is the confining pressures. For example, 50 kilopascal. So your soil pressurized. Then apply back pressures, which is also pressures, which is the water pressures, all are same. You apply back pressures, 50 kilopascal. Theoretically, it is true, but practically, it's going to be unstable. So we keep a certain pressures differences. Apply 50 kilopascal, apply 45 kilopascal only. So only 5 kilopascal higher in terms of the confining pressures. So these a little bit higher confining pressures make our soil stable, but not that in situ condition. But this is our best. Yes. One cycle has done, we increase our confining pressures, 100 kilopascal. Then inject again back pressures around 95 kilopascal. After completed second cycle, do it again. Increase 150. Inject 145. Then we can check B value, which is the increment of your port pressures by applying back pressures versus your increment of your confining pressures. Once this value greater than 0.91, consider as fully saturated. Okay, we completed third cycles, but my B value is a 0.9. Wow, so close. So we try again. Increase confining pressures 200. So your increment is 50 because the previous one is 150. Now it's 200. So the difference is the increment is 50 kilopascal. And then inject 195. Then you measure your port pressure from the machine, not your injected. Yeah, I know this is the 195. This is a known value, but systemically, we also measure port pressure inside the soils. We have another sensors. Then, let's say the development of the additional port pressure would be 45, 48, something like that. Now my p value is more than 0.95. Completed. Saturation stage completed. In terms of the soil specimen viewpoints, what is the my confining pressures? Effective confining pressures. 200? Apply 200. But back pressure is inside pressure, right? I apply back pressure into the soil, which is the 195. Outside confining pressure, 200. Effective confining pressure, only 5. Still atmospheric pressures. Of course, I know 5 kilopascal is greater than atmospheric, but we minimize the gap. This gap is a maximum 5. We can still reduce 1 kilopascal, something like that. It means that this soil now saturated, but the effective confining pressure is almost atmospheric pressures. Still as it is. Then after that, you apply consolidation pressures to create in situ stress conditions. For examples, I take the soil samples from the 10-meter from the ground surface, and my soil's unit weight is 20. Overall confining pressure is 200, right? But my effective confining pressure is only 5. Apply another 195 kilopascal in the consolidation stages. And then we are supposed to construct our shallow foundation, right? Which is for example, 10,000 kilopascal. Then after that, we apply 10,000 kilopascal in the shearing stages. So total, our trial test, we have 3 stages. One is saturation. Second one is a consolidation. Third one, shearing stages. First one is a saturation conditions to get our soil saturated. Just initial conditions. Second stages is the consolidations to simulate in situ conditions. Lastly, we apply additional load to simulate our additional footing load and building load. Then we obtain soil's shear strength under real stress conditions. Hi, Prof, how do you know CD test, CU test, UU test? It depends on engineer's perspective. This building, only 10 years plan, very short term. You don't need to do drain long term. Just conduct on drain, still okay. But you want to demolish your Marina Bay Sands building after 10 years? At least 100 years. It means that you may want to get long-term properties, right? After these circumstance considerations, you choose type of tests. So today, I just explained to you CD tests, consolidated drain tests. So after these tests, we will get some soils, the compression only, and as mentioned before, dense one, we get the heat peak value and then decreases, and then contracted and then dilated. And mostly we conduct several tests, different confining pressures to get more column failure criterions. Let's say you have only one. How do you draw? This. We have a lot of options to draw straight line, but at least you have 2 to 3. We have only one unique failure criterion. This line touch all circles. So from the CD test, we will obtain effective value, prime. We can't measure water pressure because we open all valves. This is the typical NC. This is the OC. And once we obtain C prime, B prime from the CD test, we will use embankment or stem slope stability. I will stop here. Then try to explain. Just assumption. Oh, my second quiz question is please explain CD tests. How do you explain? You have to draw this graph, these equations. Yeah. Next week, I can continue where we left off. And then before that, you try yourself.